तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we discussed the LU decomposition of matrices. So we just summarize what we learned there. That is, if you have a matrix equation or the linear set of linear equations of the form Ax equal to B, and where B is a set of solution, the right hand side of the matrix which has some numbers, and x is the unknown, and A is the matrix of the coefficients of the equation of the elements in the linear equation, and then we have Lx equal to B, and then we can split this matrix, sorry, Ax equal to B, and then we can split this matrix A into two matrices L and U. One is lower triangular and the other one is upper triangular, and then we can write this as LU, this matrix A as LU and into U, and that would transform the equations into LU into x equal to B, right? So where L is, as I said, is a lower triangular and U is upper triangular, and then we split this equations into two now. That is, we could call Ux equal to y as an equation, and then solve for Ly equal to B. So we can solve, since we know the B and the L, we learned how to actually construct the L and U matrix given the A matrix, and then we can solve for this Ly equal to B, and then use that solution y, Ux equal to y, to solve for x. That's what we learned in the last class. And we learned that when you eliminate A to make an upper triangular matrix by a Gauss elimination process, we actually construct what we construct as the upper triangular matrix in the Gauss elimination process is actually this U matrix, and the elements we use to multiply the rows and when we subtract from the rows below that to make this column 0, this column element 0, is actually the elements of the L matrix. That's what we saw, and then we saw a program which actually implements that, and then we saw this program in which we actually implemented this idea that whatever we were using as for elimination process, okay, we just store them as, so we store that factor which we use to eliminate the column elements, we store that in the column elements which itself. So now we replace the A matrix, we replace those, whatever this element was in the A matrix. Now in the U matrix that is 0, so I can store that position to store the element of the L matrix. So these positions in the matrix were used to store the elements of the L matrix, because we don't need to store the elements of the diagonal elements of the L matrix, because we take them to be 1. That's the choice which we made, and in that choice we know that these elements are simply the factors to use to eliminate these elements, and that's what was done here. So that factor was that factor x, which is used, was simply stored in that column element. And then once we have these matrices, and we could first do Ly equal to B, because we know the B, which is the right hand side of the matrix equation, and L is just is a lower triangular matrix, so we can do a forward substitution. That's alpha 1 1 is 1. So the y1 will be simply b1, and then alpha 21 into alpha 22, alpha 22 is 1, alpha 21 is known, so we can do a forward substitution and get the elements of y. Okay, and that is what's been implemented here. As you can see, I go from I equal to 0 to I equal to n. That is the number of y values which you need to get. So we need to get y of 0 to y of n. Okay, and then we say that j, there is another variable j which goes from j to I minus 1. So when I is 0, there is only one element, j is also 0, so there is only one element. So then we say that x will now simply turn out to be x is initialized to 0, so x is equal to d 0 0. Right? I is 0, j is 0, d is 0 0, and then so when I equal to 0 and j is also 0, so it doesn't actually go into this element at all, sorry. It doesn't go into this particular line, it comes out here, and y of 0 will be simply d of 0, okay, minus 0, x is initialized as 0. Right? But when I is 1, okay, now this sum runs from j equal to 0 to j equal to 0, so there will be one element here. When I is 1, okay, there will be one substitution here, okay, there is one execution of this this command. So that's x goes now from 0 to d10. Okay, j is 0, I is 0, to the d10. So now you remember d10 is actually this element alpha 21, okay, which we have stored as alpha 21 in the original matrix. D is our original matrix. So there we have stored now this alpha 21 as d10, right? So that's the element which has been stored. Okay, so that is d10 into this one. This is what we get. Okay, so this process we will get, and then we subtract that from d of I, and then we will get the y of 1. Okay, so d of 1 minus d10 into y of 0. So now we already know y of 0. So this command now basically means y of 1 equal to d of 1 minus d10 into y of 1. Right? So that is basically solving the second line of this equation. That is alpha 21, alpha 22 into y1, y2. Y1, y2 is equal to d2. That's what we are solving here. Okay, this starts from 1. Well, my program starts with 0. So that's why this actually becomes d0 alpha 0 1 alpha 1 1 equal to y0 into y0 y1 equal to d1. That's what we just solved. So we solve that, and then in similar, this is a forward substitution, and we can get all the y values from this. And once we have the y values, we go to the next equation. That is, we solve. We have the y values here, and then we go to this equation. And this we have seen earlier in the Gauss elimination process. So that is, now this is an upper triangular matrix, and these are our unknowns, and this we know now y values. So now we have to do a back substitution. So we go backwards. So we go actually backwards and solve. So now I starts from n to 0. In the forward substitution, remember we go from 0 to n. Okay, now we start from the back substitution. That way I goes from n to 0, and then we get the solution values here, and that's what we have seen earlier. Okay. So this is the way we do the LU decomposition. The advantage of this with the elimination process we saw earlier, okay, is that in the elimination process we only keep this matrix, that is U matrix, right? Basically, because we take the full A matrix, and then we eliminate these columns and make a upper triangular matrix. But then, in order to keep the equation the same, we also need to change the right hand side of the matrix. That means that the B values also to be appropriately changed. So when we change the A matrix to make it an upper triangular, we also have to change the B values. And that means that for every time for an equation we have, let's say the A is the same but B is different, then we have to find a new upper triangular matrix. So that's a kind of waste of time. Especially in cases where you have to find the inverse of the matrix, etc. We will see that later. So in this case, once you have the L and U decomposed, and simply changing the right hand side of the matrix, we can get different solutions. For example, in the case we want to find the inverse of the matrix, this will be extremely useful, as we will see soon. Okay, so now that's a complete story. U has been written as A has been written as L and U, and we have used that to solve the equations. Okay. Okay, so now before we go into the actual use of this matrix to find the inverse of a matrix, we will just look at the implementation, one implementation which we have not seen earlier, that is in the Gauss elimination, the pivoting. Okay, so one thing which we have not seen is when you had a matrix like this, okay, and then we want to eliminate all the columns here, okay, and to make the upper triangular matrix using the Gauss elimination scheme, okay, we multiply, we divide this row by this element. So this diagonal element A11 and multiply it by A21 and then subtract from this. Right? That's what we make it this as 0. Right? We saw that just again. So in that we saw that there's one drawback of this process, and that problem is that if any of the diagonal elements tend to be small, then this factor which we use to multiply this row, okay, in this case, for example, if you want to eliminate the first column, the factor which we have to multiply this row, which is A21 by A11, will become very large. And as a result, any small round off errors which appear there could get amplified. Okay. So we saw that it is, and the method would completely fail if any of this diagonal elements goes to 0. So let's say, for example, in the process of eliminating this number which we want to do, this column element which we want to do, let's say this also goes to 0. And in the next step which we want to, when we want to eliminate these column elements below the second row, we will find that we don't have a factor because the factor goes to infinity. So in that case, we said that one way to solve this problem is to actually shift the rows. Right? So if any of this diagonal element goes to 0, let's say you are given a matrix with a diagonal element 0, and then you are asked to make an upper triangular matrix. And then we can't, what we do normally is to multiply this row by A21 by A11, and then A31 by A11, etc., and subtract. But you can't do that because A11 is 0. So now what you do in that case is to switch. You find out which is the largest element in this column, right? You find out which is the largest element in this column, and that corresponding row we switch to the first one, and then this switch this to that. We interchange those rows. Yes, similarly we interchange the right hand side too. So that is called the pivoting process. So one additional step has to be done here, that is just to find out which element of that column, okay, below that row, which element in that column, okay, corresponding row, the whole column is the largest element. So I just show you a program, the same example which we were using before. So now with the pivoting, okay, so we have the same matrix which we were using before, okay, which has the right hand side as 7.65, 13.5, and 16, right? And then we would now do one more step in the elimination process. See, so this is the elimination process which I had. Okay, so we had, if you remember, that we just took those elements and then we go from k equal to 0 to k equal to n minus 1. Okay, and then we eliminate, for k equal to 0, we eliminate all the elements in the first column, okay, below the first row. And when k equal to 1, we eliminate all the elements in the second column below the second row, etc. Okay. But now before we eliminate the first column, okay, what we do is we will find out what is the highest element in that column is. Okay. So I am just using this. I am just using this array called S, which was one array called S, and I store all the elements of now I go through all the elements of that column. So I go from I equal to k to I equal to n, that is all the elements of that column below the kth row. Okay, so k equal to 0 means all the elements. Okay, and if k equal to 1, it is 1 to n, and k equal to 2, and it's 2 to n, etc. So I will go through all the elements of the kth column, okay, and I store that in this array S, okay, and then I have a, so I just print that out, that elements here, and then I have a program, I have a function called max, okay, which will find out what is the maximum value of the element of these elements, which are given, and which number it is. So I store them in an array, okay, and which element of that array is the maximum, which will find out that. This is a simple process. So this is the program which does that for me, right? So this program, to this program I pass the number of elements in that array. That is, if it's a n by n matrix like this, right? If it is an n by n matrix like this, and I'm taking the first column, so I will have n elements in that, right? So the n elements in that S array S, which will have array as S array will have A11, A21 up to AN1, and then I go through that and pairwise, and I'll find out. I'll start with, let's say, the J max as 0. I'll take the first element as the maximum. I assume the first element is the maximum. J max is max 0, and S max is S of 0. That's what I assume. Okay, and then I go through the whole array, that S array. Okay, and if starting from 1, okay, so first element is taken as the maximum. I assume that, and I look at the next element, and if this next element is greater than the maximum value, which I assume to be the first element right now, and then I switch. I make that S max as that particular thing, okay, and I store J max as J. So I'm looking at pairwise. I just look at its neighbor, right? So I start from 0 and I look at its neighbor. And the first element, I start from 0, and the 0th element has been given the status of maximum here, okay, and then I look at its neighbor, and if the neighbor is higher than itself, okay, then the status is passed on to the neighbor. Okay, the neighbor is now the maximum, okay, and if it is not, then it just ignores and look at the next neighbor, etc. So whenever it finds some element higher than itself, okay, then that status of maximum is passed on to that element, and that the number of that array element is stored in J max, okay, and it returns this J max. Okay, so here is, I also want to use this to show you that how do you write a function. So here is a function which returns an integer. So it just simply returns. So what I'm trying to say is that if I pass to this program this whole array elements as 0, 1, 2, 3, etc., it looks at which element or which row in this column, okay, is the highest, and then returns that row element, the row number. Okay, so that's what this program is doing. Okay, just goes through this S, okay, and it returns that row number. So I just want to show you that that's the way. So because this returns an integer, this function is also an integer. There is a typed integer. Okay? It is type is set as integer. So integer max, and it receives the number of column elements and the elements and the elements itself. We have put S of 3 the dimension because it's a 3 by 3 matrix I am doing as an example. So it returns that value. Okay. So once it returns that value, okay, so we go here and then we have the J max. So if J max turns out to be greater than 0, okay, so if J max greater than 0, then I have to interchange those rows. Okay, that's what I'm trying to do here. Okay, then what I do is I store all the elements in that column, okay, all the elements in that row. So I know now J max is my maximum element. Okay, so that is, if J max is 1, that means in that particular column, okay, the kth column, so k plus 1th row is the maximum. Okay, so k is 0 means that the first element is the maximum. Then I have to interchange these two rows. Okay. So what I do is I store all this elements of that row into the same S matrix here, S array, and then I transfer all this into that array, and then I transfer the S which I stored into this array. That's what I am doing here. So I am storing. I had to switch between the kth row and the k plus jth row, J max row. Okay. So if J max is not equal to 0, then I have to switch between the kth row and the k plus J max row, right? Because k plus J max is the row containing the highest element in that column. Okay. So I store the kth row elements into this S, okay, and I put in the k plus J max row elements into K, and then I put the k plus J max row elements into S here. Okay, so k plus J max elements have been put into S. Okay, so that's what I am doing here. Okay, so I switch this rows, and then I go ahead, and then similarly now I have to also switch the right hand side. Okay, so now this is a problem which you remember. Okay, so when I switch these rows here, okay, when I switch these rows, okay, this and this row I switch because this happened to be bigger than A11. Okay, so I found out Jmax is 1. Okay, so I have to now switch between this and this row. Okay, when I do that switching, I would also switch here, B1 and B2. Okay, right? Otherwise, I would be getting wrong equations. Okay, so I had to switch this also. Okay, so now that's what's been done here. Okay, so I switch also. I store the dk, and the dk is now dk plus Jmax, and dk plus Jmax is now given as whatever I have stored here in this array ST. So now that's the switching, and once the switching is done, then I go back and continue with this with the next column. Okay. I go back, and then once the switching is done, then I eliminate that column. Okay, and then go and continue. I'll just show you the implementation of this what happens when I run. Okay, so here is the initial matrix, right? So 3 to 1.1601 and 10142, that's the initial matrix, and the right hand side is 7.65, 13.5, 16. Okay, so now I looked at the first column. Okay, so that is 361. So that is 0, 1, 2. Okay, so up to this. Okay, so 361 was my first column, and now my first idea is to the first thing which I have to do is to eliminate the second row and the third row elements from the first column. Okay, that's what I have to do. Okay, so right, so but that's what I have to do. So I look at that the first column, and I see that and I look at which is the maximum element in that column. It turns out to be the second row. Okay, so since it starts from 0, there is a row number is 1. Okay. So row number is 1, and the maximum element is 6. So now I have to switch, right? So I have to switch between this row, these two rows, and that's what I do. I switch between these two rows and make everything below that 0. So that's what I have done. Okay, so I can see that the second row is now gone up as a first row. Okay, so and the second row has been eliminated, and the third row also has been eliminated. Okay, so that's what I have done. Okay, so I have switched these two rows and then done the elimination process, and then you can see I switched also on the right hand side, so you can see from here. Okay, and then now I continue that. Now I look at the next row. Okay, now when I look at the next row, again I have to eliminate things below this. Okay, so I have 1 and 3.6 here, and again I see that 3.6 is bigger than 1. Right, so I should switch these two rows. Okay, I'll switch the second and third row in the second step. Okay, and then eliminate the last row. Okay, so that's what I would be doing here. Okay, so I switched this. Okay, I found out again that the 3.6 is the largest element. So I switched these two. Okay, and I made this as now the second row. Okay, and then eliminated the last row. Okay, and again you can see that here also I switched it. Okay, so the 13.75 which is here is now gone up. Okay, it's just gone here. Right, so that is the process which you are seeing. Okay. So now we have the upper triangular matrix, and then I can do the backward substitution. Okay, so now the upper triangular matrix with the right hand side, and I can do the backward substitution. Okay, now this is a simple Gauss elimination with pivoting. Okay, and you can see that the solution I get is exactly the same as what I was getting before. Okay, so only thing here is that it is considered more accurate because we always made sure that we obtain the highest accuracy which we can get from a program, because by making sure that the denominator of the factor is of the largest element in that column. That's the idea of pivoting. Okay. So now getting back to the LU decomposition and using the inverse of the matrix. Okay. So as I said before, so that we can write the LU decomposed things as okay, so we can write a matrix A as LU decomposed like this, right? So once you're given this matrix, we can write it as LU decomposed in this form. Now our idea is now to find the inverse of this matrix. Okay, so that's, you see, so inverse of this matrix. Now how do we find the inverse of this matrix? So the way to find the inverse is the following, that we'll use this matrix A, okay, and then and we substitute for B1, B2, B3, we'll substitute 1, 0, 0, 0, 0, 0. Okay, so that gives us one solution, one set of solution x1, x2, x2 up to xn, right? and then we use same matrix, but now replace the right hand side by 0 1 0 0 1 0 0 0 0. So basically we replace the right hand side by elements, columns of an identity matrix, right? Okay. So we will get, and here the columns and the solutions here will be the columns of the inverse matrix then, right? You can see that very clearly. This matrix multiplied by this column vector gives us this. Okay. Now if this, the right hand side is the columns of identity matrix, that is 1 0 0 0 and 0 1 0 0 etc., and then the corresponding solutions would be the columns of the inverse matrix, right? So columns of the inverse matrix can be obtained by replacing this equation, the right hand side of this equation with the columns of an identity matrix. Okay, so that's what we will do. Okay, and then we will find out the inverse matrix here. So now LU decomposition is especially useful here because once we have found the LU decomposed form of this, okay, we don't have to change anything. We just have to replace these columns, okay, this column, the right hand side of the matrix with this columns of the identity matrix. That's all we have to do, okay, and this matrix remains the same, and then we'll keep getting the solution. So we'll just look at the implementation of this again. So this is a program which uses the LU decomposition to find the inverse of a matrix. Okay, so again, so we have a matrix D. Okay, we will probably use the same matrix. Okay, and then we had. Now this is the one which shows the right hand side of the matrix, right? And now I have another, so I have another one which stores the LU decomposed form. Okay, so what I do is here, so I have two matrices here. I got actually three matrix things here. We don't need to have three matrices, three arrays, but I just use three arrays for illustration. So we have this array D, okay, which is a 3 by 3 matrix, and then you have C, which is also 3 by 3 matrix, and you have S, which is a 3 by 3 matrix. Okay. And this Y will be to store those intermediate solutions, which of the Ly equal to D solutions, because we are using a LU decomposed form. So we have the matrix here, okay, this matrix D. Okay, now I store this matrix into this column C, into the another matrix C. Okay, so and then so I'll tell you why I have to do this. Okay, so I have this matrix D whose inverse I am supposed to find. Okay, so before I do anything to this D matrix, okay, I have stored this elements of this D matrix into another matrix C. So C and D are same to start with. Okay, that's the same matrix. Okay, and then I call this a function. Okay, now what I have done is I want to find the LU decomposed form of this matrix, and I want to find it only once, right? And then I can change the right hand side of this matrix equation and find the inverse. Okay, so I just need to find it once. Okay, so I just written a function which would find me the LU decomposed form. So that's a function. So I call this function with D. D is now my 2 by 2 array. Okay, now here is a program which passes a 2 by 2 array to a function. Okay, and we have seen this earlier in the beginning when we were looking at the programming part. There are three different ways actually passing a two-dimensional array to a function. Right? We could pass a two-dimensional array to a two-dimensional array, a two-dimensional array to a one-dimensional array of pointers. Okay, or we could pass a two-dimensional array to a two-dimensional array of pointers. Okay. So here I choose to use the third method that I'm using this is a function LU which takes in this D, and the order of that matrix is n is 2 here. That is a 3 by 3 matrix, 0 to 2. Okay, and this function now receives it as a two-dimensional array of pointers. Okay, so this is a function which receives a two-dimensional array of pointers. And then it does the decomposition. Okay, now how does it do the decomposition? We know, we already seen this. Okay, so it just does a decomposition by elimination, right? So it uses the elements of that array, okay, and finds a factor which we need to multiply to get to eliminate columns. Okay, that factor is here. Okay, and then store that factor x, for example, here into the element itself. Okay, so after it's gone through this particular program, okay, which actually takes in this matrix D as a two-dimensional array, okay, and then does the LU decomposition. Okay, so we take this chance to again go through the LU decomposition by elimination. We have this factors for every column, for every row we have this factor, for every row, for each column we have this factor, and then whatever column element has been reduced to 0 is used to store that factor. Okay, so that's what we have done. Okay, so with this factor, and that is stored in that particular DJK element itself. Okay, for every k, every j value, okay, whichever gone to 0, the djk element which has been reduced to 0, okay, that factor is used to that element is used to store that particular factor. That is our alpha matrix. Okay. So now only one more thing what we want you to pay attention to, and that is this, that because it's a two-dimensional array of pointers, okay, when we use those elements we need to use typecasted. Okay, so that's what this is. Okay, so this is now we are using a two-dimensional array of pointers. Okay, that's what we are using. Okay, so we have noticed the way we use it. We put it in bracket with an asterisk d. Right? So that's important. So that's how you use it, because it receives it as a two-dimensional array of pointers. We could have received it as a two-dimensional array itself. In that case, we don't need to do that. We can just use it as d straight away. So now you see, we pass this element d into this particular program, and the program use that to use that matrix and split that into L and U matrices, right? And it is stored in the same matrix. So now, because this is, as you know, all matrices when you pass, they pass by reference. Okay, so when you change it inside the program, inside this function, when I change the D matrix, okay, so that will alter the D matrix in the main program also, right? Okay, so that's why I need to store, before I pass that into this, I need to store these elements in another matrix C. Okay, so I stored that. So now after I call this LU function, okay, now the D I have is in the LU decomposed form. Okay, so my original matrix is now stored in C. Okay, which in most of the cases you may not need. This I am storing this just to check that what I am getting is actually the inverse. Okay, so I store that here. Okay, otherwise we don't need to store this. So I store that here just to check that what we got at the end is an inverse matrix. And then you have the LU decomposed program. This program is called, and it returns to me D, which is in the LU decomposed form. Okay, so now that's a structure. Okay, so this is just a store. This is a two do loops just to store it, and then we have the LU decomposition. Okay, now we will just print this LU decomposed matrix here. Okay, so now let's just look at that first. So we print that. Okay, that's our original matrix. Okay, 3 to 1.1, 6 0, 6 to 1, 1 4 2. That's our original matrix, right? And then we have the LU decomposed matrix. Okay, so now of course the first row doesn't change in the LU decomposed matrix. Okay, and I have not used pivoting here. Okay, so just first row doesn't change, and this is my LU decomposed matrix. Okay. And then I have, okay, so once I have done the LU decomposition, okay, so I just show you that. Okay, so that's a upper triangular matrix. We can take it as 3 to 1.1, and then minus 2, minus 1.2, and minus 0.366667. This is the upper triangular matrix. The lower triangular matrix then would be 1, 2, 0.333, and 1 here, and then minus 1.6667. This will be the lower triangular matrix, and 1 here. That will be a lower triangular matrix. Okay, so now after that we have go ahead and find, once you have the LU decomposed matrix, we can go ahead and find the inverse of the matrix. So the next part of the program is just finding the inverse of the matrix. Okay, so now you see what I do is I have 3 columns, right? It's a 3 by 3 matrix. So M goes from 0 to 2. Okay, now there is some M, so some integer, and that goes from 0 to 2. Okay, so that means 0, 1, and 2. Okay, so the first time when M is 0, the right hand side of the matrix, okay, is I initialize first everything to 0, and the right hand side of the matrix, that is D0, is 1. Everything else is 0. Okay, so everything else is 0 on the right hand side. Okay, D0 is 1. Okay. And then I find the solution using forward substitution here in the L matrix and backward substitution in the U matrix, and I find a solution. Okay. Now that solution I store as a first column of a matrix called S. Okay. So what I got as a solution with D0 as 1 and everything else is 0 is stored as the first column. See, M is 0 here, right? So first, the 0th column, that is the first column of the matrix SIM. of the matrix X S. Okay, that's where the solution goes into. This is the backward substitution of the u x equal to y equation. Okay. So I store that as the first column. I hope this is clear. That is that we have the m going from 0 to 2. Okay, and the first time which we take it, I put in the first element as 1. Okay, that is m equal to 0 as L is 1 and everything else is 0. And I do the backward substitution to get Ly equal to D solution, that is y is obtained from Ly equal to D, a forward substitution, and then I do the backward substitution to get Uy equal to Ux equal to y. Okay, so and I get the S, so that's the solution of the thing, and I store that as the first column, that is m equal to 0 for different I, first column of the matrix S, and then I go back here. Okay, and then I will change m equal to 1. Okay, and again when I am equal to 1, everything is 0 except D1. So that is 0, 1, 0 is my D matrix, the right hand side, and I repeat the same process. And at the end of this, once I have gone through all the way up to n in this form, I have gone all the way to 2, that is 0, 1, 2. I have the full. In S, I have the inverse of the matrix. Okay, that's what I have shown here. So once I do that, I get the inverse of the matrix here. Okay. So I have the inverse matrix. So once I have the inverse matrix, I can actually check by multiplying this matrix that I get the product as 1, 0, 0. So this is the product matrix. Okay, that is 0, 0, 0 element is 1, 0, 1 element is 0, 0, 2 element is 0, 1, 0 element is 0, 1, 1 element is 1, 1, 2 element is 0, 2, 0 element is 0, 2, 1 element is 0, and 2, 2 element is 1. So I'm getting an identity matrix on the right hand side. So now another way of checking this would be to go back and put this as my original matrix and find the inverse, right? So that's another way of checking. The inverse of the inverse should be the same matrix as I started with. That also tells you how bad is the errors in the program, okay, because of the round off errors, etc. How bad they are can be seen by this, the inverse of the inverse. Okay. So when you try to do that, you will immediately see there is a problem here because the first element here is actually 0 of the inverse matrix. Okay. So without pivoting, you will not be able to do this inverse of this matrix. So here is an example of a case where you would need pivoting. So then you will need to interchange these two rows before we proceed. Okay. So but that also brings into one more point, that why I have not used pivoting here. Okay. So I showed you how to use pivoting and why I have not used pivoting here. Okay. The reason is the following, that here we are doing LU decomposition. Okay. And when you do LU decomposition, you don't change the right hand side of the matrix, right? You're only changing you do LU decomposition, you're only changing this matrix. Okay, we only change this matrix to the upper triangular and the lower triangular. Okay, I don't change the right hand side because I use the full LU into X is equal to B as the solution, as the equation. So I don't need to change this. Right? But when I do pivoting, I interchange rows. So then I need to keep track of what happens. Okay, so I need a permutation matrix. Okay, and that has to be multiplied by B. You have to multiply B with that later. Okay, otherwise you would get the wrong answer. Okay, so if you're using LU decomposition with pivoting, you will see in the standard programs that apart from the LU, if you're using a function which does your LU decomposition for you with pivoting, then it returns the original matrix in the LU decomposed form with the upper and the lower triangular matrices stored in the same thing. Okay. It also returns a permutation matrix which you need to use to interchange this rows on the B. So that means you need to somehow store the record of what exchange of rows you have made here, okay, and do this exactly the same thing on the right hand side. Okay, that's something which I have not implemented here because it's a little more involved. Okay, I thought we will do that at a later stage in the program. So now we saw that how do I compute an inverse of a matrix using an LU decomposed form. So now we will discuss a little bit more on the possible errors which can occur in this kind of a calculation. Okay. So the one way to quantify such errors would be to just look at what is the remainder which you get if you do a solution. You take AX and subtract that from B. Okay. That means you solve this equation AX equal to B. Okay, and then you you have the solution finally, and then you evaluate the left hand side, and then you subtract that from the right hand side. Okay. And or if everything is correct, okay, then Rx should be equal to 0. So you will find that R is never 0 because of the round off errors, etc. And coming in this process, we'll always have some small error residue on the left hand side of this R. Now, what kind of values which we can tolerate as residue, okay, is another question. Okay, that depends on the accuracy you need for X, obviously. Okay, but then there's one more way of quantifying that, and that is the following. Now, if you get R as a into x minus a into x, sorry, b minus ax. That's our R, right? But if x is the exact solution, okay. So if x is the exact solution, then we will have this as 0, right? Okay. So the exact solution is, we call it x with a bar here, x bar, and if x is the exact solution, then that residue should be 0. Okay, so it will be ax bar here. So then I can subtract, okay, R equal to b minus ax and R and 0 equal to b minus ax bar, and then write this equation as this. Right. So you will find that whatever the deviation of your solution from the exact solution, okay, multiplied by A is your residue. Okay. So depending upon the A matrix, okay, if this, even it's possible that even small deviation of the solution from the exact solution can give you a large residue. Okay, that depends very much on the A matrix. Okay. Or the deviation of the solution is equal to A inverse of the residue. Okay. Right. So what it means is that if you might find that you look at this, you find a solution for X, okay, Ax equal to B, you find a solution, and then you look at the residue, and you say the residue is small. Now you say residue is small, okay, residue is small, so maybe my solution is quite good, okay, quite good in the sense that it is very close to the actual solution, right, because my residues are very small. Okay. But if you write it in this form, that is the x bar minus x is A inverse of R, you find that if A inverse is small, okay, A inverse is large, sorry, if some of the elements of A inverse is large, let's say, and then you may have residues be very small, but the solution is still very bad because the actual difference is A inverse times R, and A inverse is a large matrix. Okay. So therefore, finding the A inverse is sometimes very necessary to calculate, even when you find the solutions of the set of linear equations by elimination process or whatever other means. So now this can be quantified in other ways. Okay, so first of all, let's see how we can check the A inverse. So one way to reduce the A inverse, okay, so that is what we saw actually here. So the A inverse should not be large. Okay, so that means we should adjust our A such that A inverse is not large before we attempt to solve this equation Ax equal to B. So the one way to do that is to just simply scale the coefficients of the A matrix. The A matrix itself, you could just scale. We know that if you just multiply the whole row of the matrix, or the both right and left hand side of a linear equation by a constant factor, that is not going to change the solutions. Okay, so but it might improve the accuracy of our solution. Okay. So these are very numerical tricks that's which we should remember when we solve even a simple thing as a set of linear equations. That is, you could have large errors because of round off, okay, and that getting amplified because of these reasons. So that's one way to make sure that the A inverse is always a reasonable number. Okay, so for that one thing which we can do is to actually scale the A matrix such that the largest element in any row is 1. And then we calculate A inverse. Now, even after doing this, if any of the elements of the inverse matrix is still larger than 1, much larger than 1, okay, then there is not much we can do about this, and we call that system as ill-conditioned. Okay, so that's the definition of what's called a condition. Okay. So if the A inverse is still very large after we do all the scaling of the elements, we still get scaling such that the largest element in any row is 1. even then we get an A inverse as a large value, and then it's the whole equation is called ill-conditioned equations. So now another way to find out the condition of the matrix would be, as I said, now look at A into A inverse. Okay, now if this is not equal to 1, okay, if it's not close to 1, then we will again say the system is ill-conditioned. In that sense, the program which we looked at is pretty good condition, because we did get reasonably good values as A into A inverse. Okay, so now we could always, as I said in the earlier case, we could also, the third process would be that we could actually find the inverse of the inverse, right, and then compare with the original matrix. That's another way of finding the condition of the matrix. So there are three different ways of finding the condition, as we see. We could either scale all the elements and then look at the inverse. If the inverse is large, then it is ill-conditioned. Or we could multiply a matrix by its inverse and the inverse obtained numerically, and then see how good it is and how close to unity or identity matrix it is. And if it is not close to identity matrix, then again the system is ill-conditioned. Or the third way is to actually find the inverse of the matrix and find the inverse again. Okay, and if that is not close to the matrix we started with, again we would say the matrix is ill-conditioned for this kind of process. Okay, so now we will that condition, the concept of condition, we will now quantify it and we'll come up with a number, and that's called a condition number. So that's we're using the concept which we just talked about. Okay, that is the condition number of a matrix A is A times, it's called the norm of the matrix A multiplied by the norm of the matrix A inverse. Okay, now here is one way of finding the norm. Okay, this is a definition of the norm. I don't go into the details of the analysis here. Okay, just tell you what this is. That is, there's one way of finding the norm is just to sum all the elements of the matrix, the sum of the square of all the elements, and the sum of the squares of all the elements in the matrix is one norm. Okay, this is something which is invariant under rotations of the matrix, etc. So this is sum of the squares of the elements of the matrix, okay, and that is called a norm. And then you could compute this norm for A and its inverse, okay, and you take the product, okay, and that's called a condition number. Okay, that's way of quantifying the condition. So, right, so we'll see the use of that. Okay, so now here it is. What is the significance of this number? Right. So the reliability of solutions of the equations of the form Ax equal to B, right? So we saw that. So that's given by. So that's what we are interested in looking at, right? So we can see that as delta x by x given by condition A into delta A by A. That's the reliability of the solutions. Okay. So delta x by x is the deviation from the actual solution. Okay. So we got an x, and delta x by x is the relative error, right, in the x. Okay, so that is actually equal to the delta A by A. Okay, is a relative into condition of A. That's the relative error in the norm of the coefficients of the matrix A. Okay, now that's the connection. Okay, so delta A by A is the relative error in the norm of the coefficients of A. Okay, so now with this in our mind, okay, that we have all this ideas of having a condition number, okay, and we know how to compute the inverse. Okay, since we can compute the inverse condition number, and we can use the condition numbers to quantify the errors we have, we could try to solve some problems, and then we actually could check whether what is the reliability of this solution is in a practical way. Okay, so now here is a problem which we should be looking at. Okay, here is a set of equations, okay, which we have to solve. Now I just increase the dimension by 1. So we can see that some of the elements are zeros here. That is, this is the first row of my matrix now would be 2, 4, minus 1, minus 2. And the second row is now 4, 0, 2, 1. And the third row is 1, 2, 0, minus 1, 2, minus 2, and 0. And the fourth row is 1, 2, 0, and 5. And the right hand side is 10, 7, 3, and 2. So we could try to do the LU decomposition of that, and we could also do the Gaussian elimination with pivoting. Okay. So we could do LU decomposition without pivoting. We have the programs for that. Okay. So we could do that Gauss elimination with pivoting and LU decomposition without pivoting, and we could find the inverse. Once you have the LU decomposed form, we could find the inverse of this coefficient matrix, and then we could check what the errors, how these values would compare, the solutions would compare. Okay, and that is something which you should try to do. So far we looked at the a set of linear equations, and we used some matrix methods to solve a set of linear equations. Okay, so now we continue a little bit more on this matrix equations and look at some other properties of matrices. For example, we look at how to compute the eigenvalues of this matrices R. For example, we saw that to solve matrix equations of the form Ax equal to B, that's what we just learned. Okay. So now we would want to look at the cases where B equal to 0. Okay, the right hand side is 0. Okay. So in that case, this equation Ax equal to 0, we can't find the solution of that by looking at the inverse of the matrix A, right? So if the B is non-zero, then we could compute the inverse of this matrix A and multiply both sides by the inverse, and we get the solution of A. Okay. So we can't find the solution of this by looking at the inverse of the matrix. But we could still find some non-trivial cases. So by the eigenvalues of the problem, for example, okay, are one of the examples where we want to solve equations of the form Ax equal to 0. So it's not that B is always non-zero in the set of linear equations you are interested in. We are always looking at cases where B is non-zero. That's not true. Okay, there will be cases where B is 0. That's one example of that, is finding the eigenvalues of the matrix. So we'll see that. Okay, now that's something which you would look at now. Okay, so for example, when you want to look at the eigenvalues of the matrix A, okay, we know the characteristic equation which you would write is something like A minus lambda x equal to 0, lambda I equal to 0, right? So that is a matrix of this form. We may have to solve matrices of this form, a set of linear equations of this form, where the right hand side is completely 0, right? So that's something which we would now work. Okay, so with this again, equation of the form Ax equal to 0, right? Ax equal to B, but the right hand side is now 0. Okay, so that kind of, so how to solve equations of this form? Okay, that's what we should now be looking at. Our standard, the methods which is looked at so far, okay, will not work in this case. Right? So what we just know, that the matrix which we saw is of this form, that is A minus lambda I x equal to 0. Right? So that is a matrix A into x is equal to 0. So some matrix into time x equal to 0. That's what we are interested in solving. But what would be interested in here is actually finding these values of lambda. Okay, not actually finding the solutions. So we would be more interested in solving this equation for the lambdas. Right? So now, if you have an equation of this form, and you would think that okay, the solution of this is very trivial because x equal to 0 is a solution, right? So that what I'm trying to say is, if you have an equation of this form, Ax equal to 0, okay, that is B's right hand side is 0, then you would think that this is a trivial solution, that Ax is equal to 0, but what x is 0 is a solution. Okay. But that may not be true if the matrix, the determinant itself is 0. Okay, so that is, you have a matrix A into x is equal to 0, and I just said that if finding an inverse doesn't make sense, because if I multiply by inverse on this side I get x, but then here it is 0, so that I get only the trivial solution x equal to 0. But let's consider the case where the inverse did not exist, okay, right? Or the determinant, the inverse of this matrix is adjoint divided by the determinant, but the determinant itself is 0. Okay, that means we couldn't find the inverse of that matrix. Okay. In that case, we could have non-trivial solutions for these equations, right? Okay, so that's something which you'd be interested in looking at. So the case where this determinant is 0, and that's what we use to find the eigenvalues. So our characteristic equation for the eigenvalue would be A minus lambda I into x equal to 0. So A minus lambda, the determinant of A minus lambda I equal to 0 is the equation which you have to solve for the eigenvalue cases. Okay, so that's another form of matrix equations you are interested in. Okay, apart from just solving Ax equal to B, we might be there may be situations where we want to find the eigenvalues of the matrix. That means we want to find cases where the determinant of this is 0. So then we can write that determinant and then solve for lambda, and that is when you write down the determinant, we will have a polynomial of this form in lambda. Okay, so this is when you write the determinant of this matrix equal to 0, then we will have a polynomial of this form, and what we need to find is the solutions of this polynomial. So that's interesting. We know how to find the solutions of some nonlinear equations. We saw that only for order 2, but this will be order n. So we have to find the solution of this equation. But before we go into finding the solutions of this equation, first we have to construct this polynomial, right? So to summarize, what we want to look at is cases where you have equations of this form. That is, we have given a matrix A, and we want to find the eigenvalues of that matrix. So then we have some A equation as A minus lambda I determinant equal to 0, right? And that would lead us to a polynomial, and we want to solve this polynomial. Okay? So that's a full problem. But the first step to that would be to construct the polynomial. That is, the coefficients of this polynomial has to be constructed. Okay? What is this Pn minus 1, P1, Pn up to P0 is? So P0 to Pn minus 1 we need to construct. Thus that itself is a non-trivial problem when it comes to large matrices. Okay? So what we will discuss now is methods of constructing this polynomial and then finding the solutions of this polynomial. And then once we have the solution of the polynomial, then that means we have the eigenvalues of this matrix A, which are the lambdas, they call the eigenvalues. And then for each of these eigenvalues, okay, each of this lambda, there is a value x, okay, which would call the column vector x, which is the eigenfunction of this matrix. So that our interest would be to look at this eigenvalues and eigenfunctions. That's what we would be looking at in the coming few lectures.